All right, hello everyone. Welcome to the Friday Transportation Seminar. My name is Jenny Liu, and I'm in the School of Urban Studies and Planning, and I host this particular seminar together with my colleague, Dr. Miguel Figliozzi, over at the Civil Engineering. And today we have the last of our series of student presenters from the TRB conference, and we have two very interesting presentations coming up. So first up, we have Travis Glick, who is going to present on bus dwell times, and he is a PhD student in civil engineering. And then second up, we will have Wei Shi, who is also a PhD student in the Urban Studies and Planning School. So I will be turning over the floor over to Travis.
Hello, everybody. Today I'm going to be presenting on some research that I conducted last year regarding determinants of bus dwell times. So predicting dwell times with the given information from what is happening at a particular stop. I think this stopped working. Okay. So my name is Travis Glick. I have been at Portland State for the past 7 years and been working with Dr. Figliozzi for the past 4. In that time, I've conducted an undergraduate thesis, master's thesis, and several papers. This is one of those papers from last year's TRB. The project that we're looking at is a continuation of research regarding bus dwell times. Now, this is really important because dwell times are one of the most, probably the most contributing factor to travel time variability when looking at routes and scheduling. And if those travel times are not predictable, this leads to a schedule that isn't predictable, low user satisfaction, increased cost to the agency, which are non-desirable. So the better you can predict how a bus is going to behave at a particular stop, the better that you can schedule. And this has been studied for a long time, decades now. And in that time, mostly it's been reliant on stop level data. And this stop level data is great. It's highly accessible across agencies. Unfortunately, it had problems. And those problems are low reliability for any stop near a signalized intersection. There are so many factors that affect bus stops when they're near those signalized intersections that information at the stops specifically isn't all that helpful. And so these previous studies came with biases in terms of estimating the coefficients or the contribution of those coefficients to understanding the variability of bus dwell times. So with the introduction of new data sources, we decided to see if new variables could be applied and to see if some of those data biases could be corrected. This project looked at both individual stops of multiple types, so stops near intersections, stops away from intersections, time point stops, which are stops used for scheduling. If a bus arrives early, they wait there to be back on schedule. Also looked at broad pooled results of multiple stop types to see how the new dependent and independent variables impacted predictability. So first we have the data sources, and stop level data is still a major data source. And this tells you information about what is happening at the bus stop specifically. How many people got on, how many people got off, how long were the doors open, what was the dwell time at that stop, what time was the bus supposed to arrive at the stop versus when did it actually arrive, when did it leave. This type of information is available. It's widespread and widely used, but it comes with the flaw that between those stops, you don't really know what happened. Maybe it says that the bus was an average time of 15 miles an hour between 2 stops. Unfortunately, that could mean 30 miles an hour for half and stop for the other half, and you just don't know. These stop level data came from the following stops, which are along Powell and Route 9 for Portland, which is a heavily used route that carries people from the city of Gresham to the city of Portland. This is a very highly used segment of that road. High resolution data, the newer data set, is GPS data. So as buses travel, they leave an archive of where they were and what time it was. And in this case, that is every 5 seconds. And for that 5-second data, we can look at that and gain understanding of what's happening between stops. But high-resolution data has its own problem, which is that it does not record when the wheels of the bus have stopped moving. And so we decided to also use that interval, which is periods where the bus didn't record data for long stretches, greater than 5 minutes, minus the normal gap of 5 seconds, as another metric for how long the bus was actually stopped. And so that is a new independent variable that we will test alongside dwell from the stop level data. These data sets combined showed different things and different variables. Now, for dwell, you can't just say, what is typical dwell? It is so dependent on what type of stop and factors that are happening. For example, looking at 82nd. The 15th percentile, that means 85% of buses, or of dwell times, were above this time, 15% lower. 20 seconds. And when you look at that for that period with a max of 270 seconds, an average of about a minute, and compare that with, say, 36, only 15% of the buses show dwell times above 16 seconds, less than the 15th percentile of 82nd, a much less used stop, which, when you look at the activity of these stops, makes sense. At 82nd, it's stopping 60 times a day, 250 people boarding and alighting every day, with 3-ish lift movements, people using the wheelchair lift every single day, versus less than 1 every 3 for the lift, and 1/20th the number of boarders, with only half the number of stops. And so these can't just be directly compared. So we need to look at what is influencing those times. From the stop level data, the biggest contributors are passenger movements. Did the bus stop? That's important. So that's the stop variable. How many people got on? How many people got off? Was a lift used? Was the bus early, and specifically, how early was it? Was it a minute early, 2 minutes early? And that makes a difference in the prediction. From the combined data, we added new variables. Length, the distance between consecutive GPS coordinates. Now, loosely, this is directly around the bus stop, and this can be understood to correlate to acceleration, even though we don't have that data. If the length is very long, it means the bus was moving quicker. If it's short, typically it means the bus was moving slower. Speed. Speed, not at the stop, but immediately before and immediately after. And this is an indication of the general traffic congestion, or lack thereof, around that stop. So what was general traffic doing at that time? Near side and far side. A near side stop is a stop where you approach a stop before crossing a signalized intersection. A far side stop is the opposite of that situation, where you stop at an intersection or get through it and then stop immediately following. And these are a few bus lengths before or after a given signalized intersection. A few more important data points. Intersection, int far, and int near. Int far is the multiple of intersection and far side, int near, intersection, and near side. The intersection variable itself is an effect of the high resolution data. When recording the point before and the point after a stop, where were they? Was the point after for a near side stop on the far side of the intersection, rather than being somewhere inside the intersection or nearer to the stop? This would be a 0. This would be a 1. For far side stops, this would be a 1, where the point before the stop appeared before the signalized intersection. So for the models I'll get into, we looked at 6 plus pooled results. 3 of those models, A, C, and E. So, sorry, slight mistake. A, C, and E had no lift movements, didn't consider what was happening for the lift. The others did include lift movements. A, B, C, and D used dwell time as the independent variable and attempted to predict that first with just the passenger movements from the stop level data, and then all significant variables from both data sets. And then finally, predicting that interval time with all available data. Brings us into how did they work at individual stops. And so for those of you who don't know, R-squared is a measure of how well your model, how much of the variability in your data is accounted for by your model. So an R-squared of 0.5 means that 50% of the data variability is accounted for in the model, 0.8, 80%, 0.2, 20%. An adjusted R-squared adds a penalty for adding more variables. For example, if you had some data and you put in a bunch of random ones and zeros and added thousands of variables, by chance you might very well predict variability in the model. However, having that many variables would reduce the adjusted R-squared. So this removes some of the element of chance. If you have a strong model, generally the R-squared and the adjusted R-squared are very similar. And so I'll draw your attention to 39th. 39th is a hard stop to predict. It's a far side stop, it's a time point. And so there are a lot of other factors going into it other than just passenger movements. When you look at the passenger movements alone, 16% of the variability at that stop is actually accounted for. But when you add in the other variables from high resolution data, you end up accounting for about half of all the variability, which puts this on par with other models that have been presented in the past that traditionally excluded stops like 39th. Interval even better. For the other stops, or for the stops down below, this is a plot of their adjusted R-squareds for each of the 6 models. The thing to note here is that, for the most part, how much variability was predicted stayed fairly constant, even with the introduction of new variables for these mid-block stops away from signalized intersections, non-time points. But the assumed contribution of things like when a bus stops or how much ons mattered is reduced in some cases. So not much change with the introduction of new variables in terms of how much could be predicted. Not the case when looking at those time points, far side and near side stops. The first two, using just your stop level data, never got to 20% of the variability. When you add in how early the bus was, that intersection variable, you end up being able to predict much more of the variability. Looking more closely at 82nd, we can get into some of the biases that other models have had. That when you have a stop like 82nd that has this huge range of possible dwell times, you would see models that would only use dwell times below a certain value, others that would ignore it altogether. And as you reduce the length of total dwell time that you allow in your model, the contribution assumed of the ons and offs is assumed larger and larger, indicating a bias in some of the data sets that once you include everything, you can still have a decent R-squared, but it's understood that early and that intersection variable are much more important. So this brings us into the pooled results. The pooled results are really what we're after, trying to look at how to predict dwell on a route. And so let's start with these 3 variables, which couldn't be in the other one. Because a far side stop, for example, and a near side stop is always 1 or always 0 at any individual stop. They fall out of the model. When you add them in here, they can account for about 8% of the total variability. That far side stops and near side stops add about 7 seconds to the estimated dwell time just because of what they are. A bus bay will add a second as well, just by being there. Looking at ons and offs, you can also add in another component which is very important, which is the nonlinearity. As the number of ons increase, the number of offs increase. The amount of time that each person is going to take will fall. And so that's shown by the model that, yes, one person boarding might take 4 seconds. The next person will reduce that slightly. That 8 people alighting is likely to take about the same amount of time as 10 people alighting. And so this nonlinearity is important. And overall, this accounts for about 25% of the total variability within the data. Length and average speed, the general traffic behavior around the stop, and that metric that can give us an idea of what's happening directly at the stop, at least for that particular one. The longer the length, so the faster that bus goes, the longer it's likely to be there. For the speed, the faster the general traffic, the less that your bus is likely to dwell. So if things are moving at 25 miles per, or 15 miles per hour around the stop, you're likely to cut 7 seconds or so off of the dwell time. And then looking at the intersection, int far and int near. That intersection variable, if something appears on the far side, says it'll add a couple of seconds. But for int far, meaning that first point appears before the intersection, it's adding 25 seconds. This is an indication of the traffic light, that if that first point appears before the intersection, it's a way of capturing what would happen if the bus was stopped before the signal needing to go through. And signal data is somewhat difficult to come by and incorporate into your model, figuring out what's happening. But as a metric to get an idea of what that would do, this is what it's showing. While, on the other hand, having your next point on the far side of an intersection that is a near side stop, this is an indication that your bus made it all the way through, thus reducing the time at that intersection, or at that stop, by 5 seconds. Overall, these pooled results could capture about 55% of the total variability within the data, which is above what many other models have proposed. And for a model that includes time points, near side stops, far side stops, extremely long dwells, and down to the midpoints, mid-block stops, this is doing quite well. Seen another way, on the right side, you have the relative contribution to understanding variability and the coefficient provided by that variable. Stops, ons, offs, their squared values. Was it a near side stop, far side stop, how early it was, counts for the vast majority of what's going on. And yes, you do with stops, ons, and offs, you can capture a lot. But that inclusion of far side captures even more than ons alone. And so this data allows you to learn more and not be subject to some of the biases of other models, which often overestimated coefficients would predict much longer times for each person boarding or each person alighting. If they would often take models, remove lift events entirely because of how much they skewed data. When they included them, it could lower their R-squared. And so models that are very good at predicting what was happening stops away from intersections sometimes could only account for 1/3 of the total variability, which means that our model is an improvement. So with what we have proposed, we were able to capture more than half of the total variability within our data set. We accounted for nonlinearity of passenger movements. And additionally, by using just this data and no signal data, no traffic counts, no real-time traffic congestion, we are able to get an idea of the roadway. How does the behavior of speeds around the stop at a given stop at that moment, how is that likely to affect the dwell? And so it can capture traffic and traffic signals without having direct data. And for those of you interested, there's quite a bit more detail in the paper. Any questions? East and west. There were stops on both sides.
Okay, why did you choose that particular route?
So Route 9 is a well-studied stop, so we are able to compare our results for that particular route to results of other studies that also used Route 9. It's also data we had available at the time.
Bicycle loading and unloading, we didn't include that. There's not enough information there. Why was that?
The data sets we have no information about bicycle loading and unloading. Very hard to include something that you have no knowledge of. And some buses do this. It would have an impact, I would assume. However, again, it's not included in either high resolution or stop level data at the moment.
Is this data taken from all hours of the day or just ideal situations such as when it's not rush hour?
This was weekdays, all hours. So weekdays and weekends have different commuting patterns and different effect. Previous studies have looked at how time of day changes, that you can include a factor for the peak period for non-peak periods. And that does have the potential to improve models when you look at them. Weekends behave a little bit differently, but for these pooled results, we were looking at all-day prediction for weekdays.
What are your plans going forward? Like, where do you use this now?
So, good question. This data has applications in statistical models, looking at other behaviors of bus dwells, seeing how multiple buses might impact the dwells. There are ways to look at more routes, looking at every stop along a very large route, more data, seeing how the overlapping routes might affect dwell. There's lots of places to go.
All right, thank you so much.
When some
Okay, thank you, Travis, for the great presentation. Now I will present another different topic. My topic is valuing bicycle infrastructure in Portland, Oregon. So this study was done by me and my advisor, Dr. Jenny Liu, who is sitting over there. So we present this in this study in this year TRB. So why we want to value the bicycle infrastructures? So as many of you know, there's a lot of cities that advocates the street improvement and transportation upgrade projects in many cities. So they want to use this kind of projects and infrastructure installation to achieve the goal of increase the mobility for pedestrian and bicyclists. However, whether this kind of infrastructure will help them achieve their goals,
according to our review of literature, actually there is very few and limited empirical evidence to support that, like whether the bicycle infrastructure will have the impacts or the benefits that city wants. So that's why we want to study and valuing the impacts of the bicycle infrastructures. And also one thing I want to mention is this paper is an extension paper of our last year TRB study. So in last year, we studied the selected types of on-street bicycle infrastructure and using the residential property value as an indicator of how the consumer will prefer which whether they will prefer that certain types of on-street bike facilities or not. So this paper, if you're interested, it's already published in the TRR last year. But given the study of last year, we received lots of comments and feedback. So that's why we want to do this extension study. So something new from last year's study is, because last year we only studied certain types of on-street facility. So many of the readers are interested in, well, how about other types of bike facility, like some off-street trails or some other types of on-street bike facility? So in this study, we will particularly look at different types of facility. And another thing is, in last year's study, we find the both of ease of access, which means the proximity to the facility, and the extensiveness of bike network all contribute to the impact to the property value. So we continue to want to use these two measures, but we improve the measurements in this year's TRB paper. So the first measure is ease of access, which measure the proximity of each residential place to the facility, like how proximate they are located. Last year we used only the straight line distance, but we find there might be some problem because, for example, if you live close to an off-street trail, but as you know, the off-street trail had limited access. Even if you live close by, you might need to detour maybe half mile to the entrance of the off-street trail. So in this study, we use the network distance to account for that. The other measure is extensiveness of bike network, means in certain buffer zone, radius zone, how many miles of the facilities are in it. So this year we measure different buffer zone from quarter mile to 1 mile to see whether the residents will prefer differently for different buffer zones. For example, they might care less for like larger zones of bike, like further care less about further bike facilities, whether or not. So we want to account for that. So here is our main research goal and the difference from last year's paper. So given that, we review the literature. What we find is there are a couple of studies to look at the off-street trail, their impacts to property value are generally from positive to neutral. But there are very, very limited studies to look at the on-street facilities. We only find Rsquared and Welch did value the on-street facility, but the results are very limited as well. However, on the other side, we find there are some route choice study to look at the preference of on-street facility, but from the route choice study, they do find some preference for on-street facility. So we want to use the residential property value price to reevaluate the value of different types of facility. So that's the main goal of our study. So particularly, we look at 4 types of bike facility in Portland. So for the on-street facility, we categorize them into 2 types. One is the advanced bike facility, which we include bike boulevard, which is mostly on in the east side on very quiet streets, and the streets might have some traffic speed limit or some bump or roundabout treatment to help to reduce the auto travel volume and makes the bicyclists feel more comfortable to ride on it. So the second advanced bike facility is the cycle track, or called separated bike lane, which there are physical separation. It's like the bike lane in Broadway to separate the bicycle and autos. And the third advanced bike facility is the buffered bike lane, which it might not necessarily have physical separation, but it's draw 2 different lines on the road to kind of separate the auto and the bicyclists. So those are our advanced bike facility. And the other is, we include in the study, is just the simple striped bike lane, which don't have any other buffer or other treatment of quiet the streets. So beyond the 2 types of on-street bike facility, we also include 2 types of off-street trail. So one is the regional multi-use paths, which is like very long distance trails, and the other is local multi-use paths, which is mostly based in the parks. So here is the distribution of our four types of bike facility. So the yellow lanes are the advanced bike facility, which concentrate mostly in the city center and inner east. And the blue line are bike lanes. We can say they are more spread all across the city. And the regional multi-use path is this green lines. So they are very sparsely distributed and have long distance bring the bicyclists from one destination to another. And the last is the local multi-use paths, which are mostly located in the parks and has some very limited space in the parks. So given the 4 types introduced, I want to introduce the main methodology we learned to value these the impact of those facilities. So the method we use is called hedonic price model. So actually, it's just a regression model that uses the property price as dependent variable, and then control different independent variable to see whether the bicycle characteristics will have impacts on the property value. So beyond the bicycle characteristics, we control another 3 sets of characters, which are the transaction characteristics, the property attributes itself, and the neighborhood attributes. We want to control all the factors that might influence the property value, and then to see the particularly what's the bike characteristics will affect the property value. So that's the hedonic price model. So as many of you may think, the property value actually very easily being affected by the nearby properties. Like if your neighbor sold a high price of their house, and your house may be also more likely to get a high value. So given that reason, we introduced a spatial autocorrelation regression model, which weighted your neighbors' neighbor's property value price, and to more improve the ordinary, like the simple regression model. So that's basically two models we use. So the data we use is Multnomah County residential property tax roll data from 2010 to 2013. There are roughly 17,000 of single-family homes and about 3,000 multifamily homes. Here, the two maps illustrate the distribution of single-family home and multifamily home. So the yellow dots means the number of homes, and different color scales means the price, the average price. So we can see for single-family homes, it's more widely spread across the city. But for multifamily homes, they are more concentrated in the city center. So here is the property data we use. So as we mentioned in our hedonic model, so there are multiple different factors will affect property value. So the bike facility, like the ease of access and extensiveness of network, is our key independent variable. And given that, we also include these three other categories of factors, like the property attributes, like the age, its size, and the tax information. And the neighborhood amenities, we include its location, like distance to CBD, to city center, the school quality, the crime rate, and work score. And also the last is the transaction variables, like which year it's sold, whether it's on a recession year, and the season it's sold, whether it's sold in a rainy season or not. So giving all of those factors controlled, we use the regression model and come to these our final findings. So the regression model is very long and has lots of coefficients, and different models will present differently. So we just want to simplify the results model in this graph looking to make you more easily to understand our results. So we divided the results into single-family home and multi-family home because the factors influence these two types are different. So and we only present the bike characteristics of these four different types. So the arrows represent each 10% closer to the bike facilities will how will it affect the property value. So if it's increase, we'll have a like upper arrow. If it's decrease, we'll have a down arrow. And the numbers beside is how much like we transform the coefficient to the actual price impact. Like for this arrow, it's like each 10% closer if the house closer to the advanced bike facility will contribute $453 increase for the property. So here is how to interpret this. And the circled arrow is the extensiveness of network measure. So it's each quarter mile increase in the buffer zone, how it will impact the property value. And those four columns are using the different buffer zones from quarter mile to 1 mile. So we want to look at whether the different buffer zones will have different impacts to the property value. So here are the results. So we can see for advanced bike facilities, all the arrows for single-family homes and multi-family homes are all green up arrows, which means the closer to advanced bike facility and the denser bicycle network of advanced bike facility will contribute a positive impact on property value. Property value you can think as an indicator of consumers' preference. Like they like this kind of amenities. They like to live closer to advanced bike facility, and they like to have a denser network. So it's pretty consistent for advanced bike facility. But as we can see for the on-street bike facility, just the simple striped bike lane, the impacts are all negative for single-family homes. Although for multi-family homes, there are some positive effects, but you can see many of them are insignificant, which represented by a light color. So that's for so we can see the advanced bike facility and just simple striped on-street bike facility will have different impacts. So as for the off-street trails, for regional multi-use paths and local multi-use paths, the impacts are kind of inconsistent. There might be some positive impact to get closer, but people don't want to too dense. So it's pretty similar for single-family home and multi-family homes. Yeah, so that's we conclude from the results findings that different types will have different impacts on property values. And for advanced bike facility, people do value them, live closer them, and have a denser network of them. But for just simple striped bike lane, actually the single family home just negatively value them. But for the off-street trails, probably because the distribution of the off-street trail are very sparse, so we didn't find a consistent conclusion of what's the impact of them. That's probably the aspects we want to further investigate. And another thing is, you can see the value numbers tends to decrease with the buffer mile zone increase. So we conclude that the impact of extensiveness of bike facility generally diminished as the buffer zone increase. That's easy to think is with the bike facility more further, people will care less. They care more of the facilities close to them. So given all of the above results, we think these results provide an important policy implication to the urban planners, and consumers do prefer high quality bike facilities. And when the planners want to design the facilities for the future, they do need to consider both the ease of access and extensiveness of the network into their planning procedure. One thing that we caution is this results is just a hedonic regression model results. It does not necessarily refer the causal effect. So it's not like because we built a bike lane, it will cause the increase of property value. So for the causal effects, we need more other methods to investigate them. So that's all for my presentation. Thank you for your attention, and any questions?
Yes.
For your hedonic model, I know you take into account many factors. But I know from high school, especially for multi-use paths and bicycle lanes, that there's homeless people that try to aggregate in those areas, and that might cause shift in property values, or power lines, high wattage power lines tend to sometimes follow those bicycle lanes. I don't know if that's also taken into account there, because I bike a lot down the street block, so I know what's happening there. Sometimes it's pollution, plants that cause a lot of pollution that are built right on the multi-use path, but they're further away, down more on the outside of I know you have many factors listed.
And yeah, there do a lot of other factors will affect the hedonic model results. Particularly, actually, we just measure the two measure of bifacility, which is proximity and extensiveness. We didn't necessarily control the factors that you mentioned.
Oh, okay.
Yeah, but that's a good point that we want to maybe consider for the future study.
Thank you. It's a difficult topic. I have two questions. One, in terms of the contribution to explaining variability, what variables were at the top, and where was bifacility located? If you have to rank the variables from highest importance to low importance, what was the location of bifacility in terms of relative contribution to explaining the variability?
You mean the factors to contribute to the
what variables explain the most?
You mean these four types of facility?
No, because typically, when you read papers about real estate, a lot of the papers based on say, well, number of rooms, bathrooms, size, and so on. Those are the ones that are typically considered the most important ones. So I'm just wondering,
like which factors are mostly
comparing to those factors that are typically, what real estate people consider as added value. How significant is the contribution of bifacility with respect to those?
Yeah, so we do look at the model without the bifacilities and just with other factors. So the bifacility do increase like around, I don't remember the exact number, maybe 5 to 10% increase the Rsquared, but the thing is, it does significantly impact and do increase the Rsquared of the model. So we think, yeah, other factors are really important, but here the bifacility characteristics are also important, and it's an important contributor to the property value.
Yeah. So the other thing is, when I notice these results, because I work with traffic data, I see a lot of like neighborhood greenways to have low traffic, and people tend to prefer low traffic streets, and bike lanes tend to be on high traffic streets.
Yeah.
Where people, don't like just for the noise and other things, don't like to be located. So you think about including traffic volumes on
yeah, actually we do include the ADT, the travel volume of the streets with bike lanes. Yeah, there are lots of assumptions, like assume the travel volume will affect the proper value instead of the bike lane impact itself. But after we control for the ADT, the travel volume, the bike lanes do have a significant negative impact. So yeah, it's not only maybe the travel volume or streets environment influence the property value, but also the bike lane itself will have a negative impact. Yeah, that's what we find. Yes?
Just a couple references if you're interested. About 15 years ago, Econ Northwest did a study on the impact of development along the streetcar.
Oh, streetcar.
Yeah, and then also there was rundown for Stock and its impact on residential values. The couple ones that right across the street, a negative a block away, started to increase about $1 square foot.
Oh.
Property.
Yeah, that's good to know. Like sort of really close, that might have negative impact, but like with certain distance away, probably it will contribute positively. Yeah, that's good. Thank you.
All right, thank you.
Everybody's time this